Hello guys, this is 11.2. We're going to look at calculus with parametric curves. So first we're going to learn about how to take derivatives for parametric equations. Right, so it's actually pretty easy, right? Dy dx, let's look at the first one. Right, dy dx is equal to dy dt over dx dt. Right, it's pretty straightforward. And the second derivative is a little trickier. The second derivative of dy dx is dy prime dt over dx dt, where y prime is dy dx, which we would get from the first formula. Okay. So in this section, it's pretty straightforward, just working with some of the formulas. Now, of course, if you're interested in how we derive these formulas, you feel free to take a look at the textbook. And there are several YouTube videos that I found pretty interesting as well. All right, but we're not going to focus on that for now. We're just going to learn about how we can work with these two formulas. All right, so let's look at our first example. All right, so example one, we want to find the tangent curve to the parametric equations x equal to secant and y equal to tangent for t between negative pi over 2 and pi over 2 at the point radical 2 and 1 where t is equal to pi over 4. Right, so that's a lot of information, and it's all we need. So first, to find the derivative, we need to find the equation of the line, we need to find the slope, which is the derivative at that point. So we want to find dy dx pi over 4. Right, same thing. Okay. All right, so let's see. First, dy dx has the formula dy dt over dx dt. Right, so we need to find those. Y is tangent, so dy dt will be secant square t over dx dt. Secant will be secant tangent. All right, so simplify, we get secant over tangent. Okay, and evaluate that at t equal to pi over 4. So we get secant of pi over 4 over tangent of pi over 4. So secant of pi over 4, that's radical 2. And tangent of pi over 4 is 1. That gives us radical 2. Okay? So that's the slope of the tangent line, right? All right, and then we want it to go through the point radical 2, 1. So to use point slope form, we can do y minus 1 is equal to slope times x minus radical 2. And if we multiply it out and then move the 1 over, get y is equal to radical 2x minus 2 plus 1, which we get y is equal to radical 2x minus 1. Okay, done. All right, next let's look at how we can integrate to find areas. Okay, so let's say what we want to find the area of this asteroid. You can see that it's very symmetric. It looks very nice, right? So what we can do is we can actually just cut this into 4 pieces, and then if we can just find one piece like that, and then we can multiply that by 4. Okay, so if you look at the purple area, that's just the area under the curve, right? So if we can think about this as y is equal to f of x for this function, for just this segment of the blue line, then we can represent the area like this. Area is 4 times the integral for x between 0 and 1 of y dx. Right? If we want to rewrite this in terms of the Cartesian function, then we're using y and dx. But since now the functions that are given to us, they are in parametric form, so we have to replace y and dx respectively. All right, so let's see. First, we know y is sine cubed. Okay, so dx will be the derivative of x, which will be 3 cosine square t times negative sine t. All right, and since x is equal to cosine square t, right? And we need to also redo the bounds. So if x is 0, that means 0 is equal to cosine 3t. So t would also be equal to 0. Now when x is equal to 1, 1 is equal to cosine cubed. That means we are looking at, oh, sorry, not 0 for cosine. We're looking at pi over 2, right? Pi over 2. And then when 1 is equal to cosine cube, this is when t is equal to 0. Okay, so our bounds is going to change as well. Okay, now let's rewrite our definite integral with new bounds and write it in terms of t. Okay, so 4. Now the new bounds going from 0 to 1. Now 0 actually corresponds to pi over 2, and 1 corresponds to 0. Okay, and then we have y dx. So y is sine cube, and dx is 3 cosine square t times negative sine t dt. All right. So the first thing, I'm gonna bring the 3 to the front, multiply with the 4, and I'm going to flip the bounds to go from, change that to go from 0 to pi over 2. And when I do that, the integrand is going to change signs, right? Meaning, well, I can just ignore this negative sign right here. Right? So everything will become nice. And that looks like sine to the 4th power t times cosine square t dt. Okay. And here we're going to use the double angle formula for cosine to simplify it. So the double angle formula we're going to use is sine square is equal to 1 minus cosine 2t over 2. And cosine square is 1 plus cosine 2t over 2. All right, so what we have here, we can rewrite this as 12 times sine to the 4th, so it will be sine square square. So 1 minus cosine 2t over 2 square times cosine square, which is 1 plus cosine 2t over 2 dt. All right, so let's multiply it out. So denominator will be 4 8, so we can bring out the 1 over 8 to the outside and simplify. We have 3 over 2. And on the inside, right, I'm going to save us some time in that when you multiply it out, right, we'll get 1. Oh, let's write out the first line. 1 minus cosine 2t plus cosine 2t square times 1 plus cosine 2t dt. All right, and then multiply it out. All right, we'll get 1 minus cosine 2t minus cosine 2t square plus cosine cube 2t. All right, now from this point on to integrate it. All right, so to integrate, the first two terms are pretty straightforward. Now the third term and the fourth term, they will require some trig integration techniques from chapter 8, which I'm pretty sure you guys still are pretty familiar with. Right, so I'm just gonna save us some time, and then if we integrate it, we get 3 over 2 times t minus 1/2 sine 2t, right, minus 1/2 t plus 1/4 sine 2t plus 1/2 sine 2t minus 1/3 sine cubed 2t, and then we'll have to evaluate those from 0 to pi over 2. All right, so let's see what we have. All right, 3 over 2 times pi over 2 minus 0 minus 0 minus 0, right? And minus 1/2 times pi over 2 sine of 2 times sine pi 0 plus 0, and then 0 0 0. That should be minus 0 minus 0, right? Same thing, right? All right, plus 1/2 pi over 2, that's 0, minus 0, and then 0 again, minus 0, and then plus 0. Okay, load up a bunch of zeros. All right, so let's see what we have. 3 over 2, pi over 2 minus pi over 4 plus 0. All right, that's easy. It's 3 pi over 8. Okay, and done. That's the area of the asteroid. Even though it's a little longer, but we can see that a lot of the technique in here we have seen before already. For example, how to take the integration of cosine square or sine square in that case, right? We use the double angle of cosine, right, which can be found up here. Very useful little formulas. Okay. Okay. All right. Next, we'll be looking at how to find the length of C, right? The length of the path from parametric equations. All right, so let's look at the definition. If a curve C is defined parametrically by x equal to f of t and y equal to g of t, where t is between a and b, and f prime g prime are continuous and not simultaneously 0 on a and b, and C is traversed exactly once as time increases from A to B, right? So traverse exactly once, meaning it's not going to repeat itself like, running on the track, you go round and round, right? So it's not going to repeat itself. Then the length of C is the definite integral, A to B square root of f prime squared plus g prime squared. Right. So, and again, we're not going to worry too much about how we derive this formula. We want to focus on how we can use it first, and then we'll work on, if you guys are interested, we can look at a little more on how we derive the formula. All right, so let's look at our first example. All right, let's start with something simple. Using the definition, find the length of the circle of radius r defined by parametrically by this set. Right. So basically, we want to just find the circumference of the circle, and let's see if we get the same thing as what we have done. All right. So from 0 to 2 pi. Right. So length is going to be equal to 0 to 2 pi, and then formula square root. Oops. Square root. So f prime. So f represents the parametric equation for x. So that will be dx dt square plus, and g prime will be dy dt square, and then dt. All right. So let's see. Dx dt. Let's work it out on the side. That's negative r sine t, right? And then dy dt will be r cosine. And you can see that sine and cosine, they work very nicely together. All right, 0 to 2 pi square root. Okay, so dx dt square will be r squared sine square plus dy dt will be r squared cosine square t. All right, I already see something nice we can simplify. All right, so 0 to pi. Factor out the r square. All right, I get r. And then sine square plus cosine square is just 1, right? Actually, let me not skip too much here. So factoring r square, I have sine square plus cosine square, which is equal to 1, right? And then square root of r square would just gives us r, right? dt. Right, and keep in mind that r is the radius, which is a constant, right? So integrate that, right? I get r squared over 2 going from 0 to 2 pi, which gives us 4 pi squared over 2. Oh, sorry. Oh gosh, what am I doing? I just said that r is a constant, so that'll be RT. I go from 0 to 2 pi. So that'll just be 2 pi r minus 0, which is 2 pi r. Right? And 2 pi r is essentially the circumference, the formula for the circumference of a circle, right? And proven parametrically. Next, we are going to look at area of surface revolution for parametrized curves. Right? So just like our regular function, we have some sort of formula to work with. Right? So here we go. If it's a revolution about the x-axis, then we have this formula here, right? 2 pi y on the outside. And then inside it's the same thing, dx dt squared plus dy dt squared. If it's revolution about the y-axis, then we have 2 pi x on the outside, and then again, the same radicals. All right, so let's take a look at an example together. All right, so example 9, the standard parametrization of the circle of radius 1 centered at 0.01 in the xy plane has this parametric equation, right? X equal to cosine and 1 plus sine for y. Right? And what we want to do is we want to use this parametrization to find the area of surface split up by revolving the circle about the x-axis, right? So essentially what we're looking here, right? So imagine you have a disk, right, sitting on top of a stick, and then you want to rotate that disk around that stick, like what we have seen in the picture, right? So we want to revolve this about the x-axis, meaning we're going to use the first one, the first formula. All right, so here we go. The surface area of revolution has the formula integral, well, that looks like another s, right? From a to b, 2 pi y square root of dx dt square plus dy dt square. All right, so we know that it's going to go from 0 to 2 pi. That will be our bounds. Y is 1 plus sine, right? That can go here, right? So let's worry about dx dt and dy dt. Dx dt is negative sine d, and dy dt is cosine. Right? You can see similar pattern like what we saw before. Right? And we can assume that a lot of things are going to disappear. All right, that's going to go from 0 to 2 pi, and then 2 pi times y, which is 1 plus sine t, and then multiply by sine square plus cosine square dt. Right? And again, that whole thing in the radical will go to 1, right? Which is very nice, right? Saves us a lot of time. So let's see what we have here. Essentially, we are doing 2 pi and then integrate 1 plus sine t from 0 to 2 pi. Okay, and that'll be equal to 2 pi times t minus cosine t going from 0 to 2 pi. Okay, all right, and let's just evaluate those. I have 2 pi and 2 pi minus 0 plus 1. Right, I'll be oh, sorry, no, 2 pi minus 1 minus 0 plus 1. Right, so the 1 cancel out. That will be 4 pi square. Okay, which will be the area of the surface of revolution, like when you rotate a disc, right? So rotate a circle, right? So it will look like a donut, except for the donut hole in the middle, it's really it's just a point, right, as you're going in towards the center. Right, so applying the formula, it's not that tricky. It's not even fun at all. I mean, it's just plug-in formulas, right, and taking derivatives and stuff. Now, there are a few things that I'm skipping from this this section. For example, in textbook example 7 talks about centroid, and that's one topic we will cover if we have time towards the end of the semester. And I believe you will see that in Calc 3 again, so there's no hurry to cover that as of now. All right, and that will be all for 11.2, doing calculus with parametric equations. Thank you guys very much, and I'll see you next time.